Let's walk through the process of making a prediction with a neural network. So we're given a pre-trained neural network. In other words, this neural network has already been trained using the stochastic gradient descent process. And in that training process, a bunch of weights were learned, so W1, W2, W3, W4, W5, W6, as well as biases B1, B2, B3. And you could think of these weights as like the m in the mx plus b equation. You can think of these b's as the b in the mx plus b equation. And the way it works is given each previous layer, whatever the input value is, that's the x value, you multiply the m value of the line with the x value, and then you add the plus b. And you keep on doing that through all the layers for all the nodes until you get an output value. Another important detail, though, is that if you do that a lot, you're adding up a bunch of linear equations. So in addition, there's an activation function which is applied to each node. So that's a lot of words. Let's walk through an example so that you can see what I'm talking about, and it should make more sense. So in this example, we're given a neural network that, given as two inputs, the weight of a person and the height of a person, it predicts the gender of that individual. And the gender prediction is a probability value between 0 and 1. In this case, we're going to say that a value of 1 or 100% corresponds to the gender prediction as female, and a value of 0 or 0% corresponds to a gender prediction of male. And like if it predicted 80%, then it's pretty confident of female, but not 100% confident. It's 80% confident. So let's walk through an example here. So this first hidden node, H1, let's calculate its value. So it's going to be this weight, or this m, times this x, so 5 times 100. And then we add that to this edge also coming into H1, so that's 3 times 50. 3 times 50. And if we add that up, that's 500 plus 150, so 650. So the value of H1 is going to be 650. So let's write that here for our purposes. The value of H2 is the same thing. So we have negative 2 times 100, negative 2 times 100, plus 1 times 50, 1 times 50, and that gives us negative 150. One important detail, though, is that for each node we apply an activation function because, as I was saying earlier in the video, if we just add up a bunch of mx plus b's all throughout the network, and we keep doing that for every node, at the end of the day all you're doing is adding up a bunch of mx plus b equation. And if you remember from algebra class, if you have a system of equations with a bunch of linear equations and you add up all of those linear equations, you're going to end up with another linear equation. You're not going to suddenly get like a x1 to the 50th power from that. That doesn't happen because you're just adding it or subtracting the equations. And because that's what we're doing here, if we don't do anything else to the network, it's just going to make a linear output, which could be okay, but it's not learning really complex patterns in the data, which might be nonlinear patterns. So to get around that, what we do is we apply activation functions to each hidden node. And a very common activation function you might have heard of is called the ReLU activation function, and it's a very simple activation function. So ReLU of x is equal to max of 0 and x. So for example, if we apply ReLU activation to H1, which we do because we do it for every hidden node, it's going to be the max of 0 and 650, which is max of 0 and 650, which is 650. So okay, H1's value is 650. In the case of H2, however, we have ReLU of 150, which is the max of 0 and negative 150. Sorry, ReLU of negative 150. So that comes out to be 0. So the value of H2 is not negative 150, but because we apply ReLU activation, it is 0. Finally, to calculate the output, O1, it's the same process, so -1 times -1 times 650 plus 2 times 0, which equals -650. And that's great, except that we want a probability output at the end, not a number. So we tend to apply an other activation function to the in binary classification, which is this case because we're predicting two things. We apply another activation function called the sigmoid activation function. So this is the sigmoid activation function. It's 1 over 1 plus e to the negative x. And it gives us, for any real number, a value between 0 and 1, which is useful for getting a probability distribution. So O1 is really the sigmoid activation applied to -650. So sigmoid of -650, which, going back to this equation, is 1 over 1 plus e to the 1 over 1 plus e to the 650, because negative 650 is positive 650. I'm going to type this equation into Google to get the output, and that gives us this very tiny number. So this is equal to basically, basically 0.0000.5111. Delete this. It's a very tiny number. Basically, it means it's predicting a value of 0 with very, very high confidence. In other words, it's predicting male given this input, which, given that input. And so that is how a neural network makes predictions. Again, this neural network was already trained before we started making predictions with it. So in the next video, we'll talk about the process of training a neural network. Thanks for watching.